And probably I start today lecture. Okay, hello everyone. So this is the second talk for the second Romania and Hong Kong Radio School. Thanks for joining us. And today I would like to show you some observation based on this white color small radio telescope at the back, and also demonstrate some simple data processing about the data that we collect based on this small radio telescope. Okay, then before I show you the observation, I would like to finish a small part that I didn't finish last lecture one. So let me move on. Yeah, here corresponding to the wedge that we discussed last week. So I hope you still remember that last week we introduced some simple terminology such as the polarization, linear polarization, luminosity, flux density, and blah, blah, blah. However, I did not show you the last picture, okay? Because here it is important, as you know, radio astronomy, sometimes the image that we collect not very beauty can compare to the optical image. The reason is we are not concentrate on the image for single dish because we have poor resolution. Secondly, the main point is we only have a few pixels for the small radio telescope. I will show you all those details. However, at least I would like to show you this figure 7, talking about different bands for the same celestial body on the sky. For example, this figure 7 corresponding to the radio, sorry, this is our own galaxy, the Milky Way galaxy. For optical, probably in Hong Kong, very difficult to take a picture for our own Milky Way galaxy. But still, we have some expert or amateur, they can take picture in some specific day, probably a fine weather sky. We can also get a beautiful Milky Way galaxy in our Hong Kong. I don't know in your country, okay? I think Singapore is not easy in some sense because which is located in tropical region, okay? Maybe Romania is much better. Anyway, here this figure I want to show you that if we take the image based on probably not single dish, maybe an array, and we got this radio picture. This is infrared, here corresponding to X-ray. So this is called multi-wavelength sky or multi-wavelength observation. So in some time, some big project all over the world, they will try to work together. I still remember a competition about doing the observation for the BO lab object on the sky. They try to use many different other bands at the same time to do so-called synchronized observation. The reason is they want to know more information about that object on the sky. All right, I'm not talking about this picture. I just want to at least show you some picture, okay? Otherwise, someone will complain why your radio astronomy class without any colorful images, okay? Yes, for radio astronomy, this is one of the reasons that our local Hong Kong student didn't like about that. You see, the picture that we create relatively not very high resolution and also not beauty. This is the point. However, if you focus on science, sometimes not beauty is not a problem. We are working on science. Sometimes we give up the beauty, but we can know more result based on our small telescope. All right then, and one important remark is so-called the B sub nu and S sub nu, this formula. Let me highlight it, the flux density. I hope you can see my cursor to indicate S sub nu equal to B sub nu times the solid angle, and where S sub nu is called the flux density, and this is a usual unit used in our radio astronomy fields. So if you have a chance to do some observation, go to some observatory, the local astronomer sometimes may ask you, what is the minimum sensitivity that you want to detect? Probably you can tell them the flux density, let's say around 20 Jansky, 2 Jansky, and or 2 micro Jansky, something like that. Okay, then we move on to another important remark that I would like to talk to you very brief, the emission mechanism, so-called emission mechanism. Maybe you say, Sing, you teach me that we can use some parameter to measure or to quantify the signal or intensity that we detect from the sky. However, where they came from? This is a good question. Okay. So in the following discussion, I will focus on some simple classification in terms of what we so-called continuum process, and spectralized process. And for this continuum process, we will say we look at the emission across a wide range of wavelengths, and this is called continuum process. So you can imagine we will show you some figure, the y-axis corresponding to intensity, or you can regard it as flux density, and the x-axis corresponding to the frequency. And this is called continuum spectrum and continuum process. But at the same time, if we focus on a particular wavelength and look at the intensity or the shape for this particular wavelength, is there any shift or any interesting shape? Probably we call it a spectralized process. So usually when you go to the observatory to do observation, the local astronomer or the corresponding staff will say, which type of process will you ask to do observation? Is a continuum observation or spectralized observation? Okay, apart from this simple classification, okay, I mean classify the process that we observe into two types, either continuum or spectralized observation. And we also commonly use to say the process is for the emission mechanism of the celestial body with respect to thermal radiation or non-thermal radiation. So I will briefly introduce the process corresponding to thermal or non-thermal radiation. These are the simple emission mechanism for those celestial body that we are interested in radio astronomy. Okay, may I remind all of you, maybe all you know that in 1888, Hertz, he made an experiment to produce some spark between two plates, and then the oscillating current introduced by these two plates then generate the electromagnetic wave. All right, and so I won't repeat this simple experiment, or I can, but you can easily to search it from the internet. So that's why we memorize his great contribution nowadays. When we use the unit for frequency, we memorize Hertz. However, what I wanted to say is, how come the electromagnetic radiation produced based on some electric charge particle? Here, if you look at figure 1, and may I remind all of you, the description, major reason I put here is for my remark. when I talk to you, I'm not asking you to look at all those paragraph details because I sent you already the corresponding document. And so you can read it at your own spare time, but pay attention for all those figures. Like figure one, and we would like to demonstrate what would happen, for example, if we have a charged particle at the center, if this is static, all right, I mean, not moving, okay, static, and then you can see this charge can produce these electric field line in this format. At left is the electric field radiating out from a charged particle at rest. However, if this charged particle, which is not static, let's say have a movement, okay, suddenly move and come back, and then you can see that the electric field line will have another shape, not like the case for the at rest. It is like here for simplification, we illustrate into this format. So a disturbance for the fields. So you can imagine a charged particle, they have acceleration or deceleration, they will provide some electromagnetic radiation. So you can imagine if you can force an electron move backward or how to say forth and back, oscillating backward and forwards, probably they can produce electromagnetic radiation. So this is one of the reasons that why in our sky we can detect some signal corresponding to some celestial body. Okay, then we start to talk about continuum process. As I mentioned before, we have continuum process and we have specialized process. And then we will introduce what we so-called thermal and non-thermal, okay, for the first part of today's my presentation. And then the second part, I would like to show you some observation and simple data processing. Now we move on to continuum process, okay. And as you see, the emission, let's say not focus on single wavelength. If we are looking at all wavelength, wide range, and what will happen? What will happen? First, we would like to introduce the back body case. In any object, the constituents atom. And what does it mean? Which means for any object, they have the negative charge electron and also have positive charge proton and etc. They form an atom. And if they are in very low temperature, or they should have a constant state of motion for this non-zero, due to non-zero temperature. Anyway, higher than absolute zero temperature, then let's say even higher than that a little bit, they have a constant state of motion, but this is very small motion. Usually we call it thermal energy. This is called thermal energy. Okay, suppose we heat up the object, and what will happen? Okay, originally the object have this constant state of motion. If we heat up and add heat to it, and of course this motion will become more rapid, okay, more violent, and so they keep on to heat on it, and this charged particle will continue like the case as I mentioned. They have a charged particle and they move. That's why they produce the electromagnetic wave, okay? But the same object, they will also absorb, and again, we keep hitting on it, so we emit inside a dense object until they finally leave on the surface. And such that radiation, we call it, I should say in this way, these cases until they getting equilibrium, and this method is called or we term on it a back body radiation. And we usually use this type of emission mechanism to explain for our optical astronomy the surface temperature for the star. And why? Okay, maybe look at the graph much better. Dense hot object, a dense and hot object will therefore emit light based on the previous discussion, because we add heat on it, and so that the constant motion for the object will become rapid, and finally they will radiate out until they leave the surface of the object and keep an equilibrium temperature. And how come we can describe on it? And scientists found in such situation, they can form what we so-called the backbody spectrum, and which means the radiation based on the backbody cases that we discussed. You can see this diagram on the y-axis corresponding to the intensity, and the x-axis corresponding to the wavelength. And please pay attention for the unit. For y-axis here up to 10 to the power 14, and for the x-axis, this is nanometer, however, times 10 to the power 3. So let's say this is 1 times 10 to the power 3 nanometer. Is it clear? Is it clear, the unit and the corresponding number? All right, and this is the so-called backbody spectrum. And based on this backbody spectrum, and we can point out one interesting result, and so-called Wien's law. And this is a continuum spectrum, and then we pointed out at the peaks wavelength. If you look at this law, T move to the left-hand side, then lambda times T equal to 0.0029. Where? Pay attention. T is in Kelvin, and the lambda, which is used meter. Okay, and such representation for this backbody spectrum, we can regard it as thermal radiation, thermal emission radiation. Okay, maybe we look at this simple question. Okay, what temperature backbody would produce emission which peaks in radio spectrum at a wavelength 10 cm? 10 cm. Okay, you can look at here the x-axis for 10 cm, of course, 10 cm. This is nanometer, okay? So for example, here 2.0 times 10 to the power 3 means 2 times 10 to the power minus 6 meter, because nano, small letter n, corresponding to 10 to the power minus 9. Okay, if you come back to this question, the question asks you which peak in the radio spectrum at a wavelength 10 cm. So you can plug it into this simple equation or formula. For lambda maximum, the wavelength equal to 0.1 meter, you plug here, and then you can easily to calculate the corresponding temperature. So the answer is 0.0029 divided by 0.1, and what we get, we will get the following result: 0.0029 divided by 0.1, and then we will get 0.029 Kelvin. So this is barely above the absolute zero, which shows that all backbody radio emission is usually the long wavelength tail of emission produced by the hotter backbody. So why we select 10 cm to all of you, and here this 10 cm, if some expert, they work on solar radio physics, 10 cm band is an important band, can indicate our sun's activity. All right. Unlucky that in Hong Kong we don't have this band, but this band closely related to the sunspot activity. So if we have a telescope, radio telescope detect this 10 cm, and we detect very interesting signal, probably has a close relation to the sunspot, and the sunspot, of course, corresponding to the solar activity. And for this black body radiation, in history, we also can, historically, we can also know that on the short wavelength side, they can simply follow what we so-called Stephen-Boltzmann law, which means the total flux of a black body is equal to a constant, so-called Stephen-Boltzmann constant, sigma, times temperature to the power 4, temperature to the power 4. And you see, to the power 4, this is very large value. If you put temperature equal to 100 kelvins to the power 4, can you understand the order of magnitude increase much? And so that's why increase rapidly on this side, on the short wavelength side. All right, this is the Greek letter sigma and Stephen-Boltzmann constant. However, the final equation we would like to present here is what we so-called Planck function. Planck function a bit complicated because the scientists want at that moment they would like to they know this spectrum. Of course, they want to find an equation to describe such property, and this property involve short wavelength and long wavelength. If we in terms of wavelength, and also you can see that the wavelength and frequency relationship is reciprocal. So on long wavelength corresponding to the lower frequency, and here corresponding to higher frequency. And finally, they form a formula, so-called Planck function, to describe such representation for this behavior. For this equation, we would like to say a few words about that, because you can see that we have many constants, such as H, so-called Planck's constant, and also have K, Boltzmann constant, right? And C for the speed of light. So you can see that this equation closely related to the quantum physics, all right? And they can describe the black body spectrum. However, for our case, for radio astronomer, they may major focus, just like this example, 10 cm. Here is 2 times 10 to the power 3 nanometer. If you keep going and up to, you continue to count on it, you can see that 10 cm may be in this size, maybe in this position, okay, maybe in this position. So bear in mind this important Planck function, very useful for our discussion. However, you see so many constant, and once you know the wavelength or the temperature, probably we can easily to plot it. And bear in mind the Planck function without only one shape. For different temperature, the P will be moved, all right? If you plot it again for different temperature, then you can see that the shape will be shift, or we call it skirt to the right or to the left. So please bear in mind, not only one shape. And now next, as we mentioned before, the radio astronomer, they major focus on this side, so-called the low frequency and long wavelength. And in such cases, we can do some simple mathematics. for approximate this term so that we can rewrite the Planck function as this format. And when we can rewrite into this format, for example, if h times c, h here we represent it based on hc divided by lambda times k times t. As you see, this 1 over lambda can be rewritten into frequency. So the Planck function times frequency we got as the energy for the photon. If the energy of photon is very, very small compared to the thermal energy k times t, here we can eliminate into the following format to get such representation. Let me see whether I can show you this representation. Let me make sure I copy it correctly for this Planck function 2hc square. Okay, yeah. Here is another representation. As you know, let me show you one more step. We can either represent the Planck function in terms of the wavelength or the frequency, right? Depends on which one you like to use. Maybe I sub nu. Okay, we can regard as B sub nu and I sub lambda and B sub lambda here. Okay, let me move on to look at the lambda case. Lambda case 2hc square over lambda 5. I use nu frequency. I apologize. Not wavelength. I use this one, and then you can see here, as I mentioned before, if h nu, let me use other color, is h nu, okay, corresponding to the energy for the photon, which is smaller than very compared to the k times t, the thermal energy, okay, which is very, very small, very small. What can we do from mass, from simple Taylor expansion? Okay, e to the power something, we can maybe, I hope I remember it correctly, okay, something like that for approximation, linear approximation. Probably we can rewrite into this format, into 1 plus, okay, we got e to the power h nu over kt, h nu over at as an object, and then park here, and so we will get 1 plus h nu over at. Am I right? And this one cancel, okay, and so what do we get? We will get kt over h nu, kt over h nu, right? And then we cancel out the result. Nu cancel here become 2, and so we can got this result. So this is the approximation when we talk about the long wavelength side, and we call it Rayleigh-Jean's tail in radio astronomy. Rayleigh-Jean's tail. So let me show you back. That's why we got these two results, depends on frequency you use or the wavelength you use. So previously, I showed you the case, the biselect temperature corresponding to 2 times nu square kt over c square, right? 2 times nu square times kt over c square. Can you follow? Okay. Now, why you do an approximation based on this blackbody spectrum on the so-called Rayleigh-Jean's tail and long wavelength? Because our radio frequency major focus on this part, and when we discuss about this part, what will happen? For example, here we have two figures. figure 3, we have two figures. If you look at the left-hand side figure, and you see for 10, for the previous question, 10 cm, 10 cm here means roughly this position. I cannot work out anything on this website. Okay, anyway, 0.1. But you see these two scale, which is linear. So you can see that 0.1 compared to 0.2, 0.3 up to 1, you are very difficult to distinguish about that, right? However, if you use some simple math skill, if I taking log, all right, on two scale, what do we get? We have on the left hand side, we get a linear scale. But on the right hand side, we have a log scale, log scale. And for this log scale, you can easily to calculate the slope. And of course, for high school math, we tell you for this straight line, roughly this is a negative slope. And you can count 1 grip, 2 grips, 3 grips, and 4th grip. And here with 2 grips, so 4/2. So the answer is -2. Can you follow the gradient -2 on this right-hand side figure corresponding to figure 3, part B, based on log scale? So we can plot the spectra against frequency, of course. This is the, how to say, this is the intensity against wavelength, right? And we get negative slope. If you change wavelength into frequency, then this is 1/it. And at that case, the line will be reversed, become positive slope. Can you follow? So if this is intensity versus wavelength, and you use log scale, you will get a negative slope. If you reverse it, you will get a positive slope. Can you follow? Can you follow? All right, and so in radio astronomy, the Weierstrass temperature for this thermal case, okay, the temperature that you calculate once you know B, let's say, and the frequency also you know, and you will get the temperature, and this temperature is a physical temperature for this case, if you base on backbody radiation. Okay, and also here is called the Weierstrass temperature. And now we move on. Here, this is more advanced looks on how come we can derive the from Planck function to get the corresponding Weierstrass temperature. And I don't go through it because I talk to you, and you can refer to the lecture notes, okay? And now here, I would like to say something why I introduce this backbody case to all of you, because usually we will talk about this diagram, figure 4, and here is let's say this is a schematic representation for the radio spectra for different number of astronomical source, and we taking out this diagram from another famous book, which was written by another professor, Carus, okay? And this is a very classical radio astronomy book. So any radio astronomy lover, they probably have one, okay? And again, look at this diagram scale. This diagram, the x-axis corresponding to frequency and the y-axis corresponding to the flux density. And I told you last week, the flux density can be detected directly based on the radio telescope, and the unit is JY, Jansky. Okay, and on this diagram, what do you notice? You should notice some line, for example, like moon, like the moon, the line. This is an entire line in this direction with positive slope. Am I right? And for Jupiter, very interesting, they have negative slope and also roughly a flat case, okay, means the slope tends to 0. And here going up, positive slope. And what I would like to remind you, for the case like quiet sun, what does it mean? You can imagine for solar physicists, they classify that our sun have a cycle, sometimes with quite inactive, not like nowadays. Nowadays is the starting of very active stage. So here would like to remind you for the quiet sun, they follow this result. So based on what we talked to you before, for the thermal radiation, the moon or the Orion Nebula M42, all right, and partly not all, because on some higher frequency, the result for this Orion Nebula will be flat. So, okay, you major concentrate for this positive slope. This is satisfied to what I introduced for you, radial genes tail approximation. So this is a spectrum. This is a spectrum. So when you got such result, you know that some of the object that we detect, which is follow the emission mechanism, so-called thermal radiation back body. So quiet sun, moon, and part of the Orion Nebula M42 and Jupiter, okay, in some sense. Can you follow? Can you follow? However, you may say, okay, Sing, I know thermal. How about the sky background and Cassiopeia A and Virgo A? And capital letter A, may I remind you here, all of you, A indicate the brightest or the brightest discrete radio strong source. So capital letter A corresponding to the strongest radio source on the sky. So class A, Virgo A very famous, which corresponding to M87. All right, few years ago, the first black hole picture based on the EHT telescope, Event Horizon Telescope, they show you the first picture corresponding to Virgo A. All right. Okay. Now, so here, if you look at this question number 2, which are the objects shows evidence for back body spectra in this figure 4, I kick out the answer and discuss to all of you. And this is what I mentioned before. The higher frequency part of Jupiter spectrum appears similar to that of back body, as does the lower frequency of the Orion Nebula. So if you use lower frequency detector to detect the Orion Nebula, they also got this result. And the spectrum of the sun is not a straight line, but it does have a broad property of increasing in high frequencies. Okay. And then now, number 3, asks you calculate the slope of the lunar spectrum from figure 4 using log units for flux density and frequency, and to check whether it is positive to light that of the black body we introduced. So for the case, the moon, okay, if we calculate it roughly, okay, now let's say maybe I say it this way, okay, due to time limitation, okay. And now this is the log plot for the flux density against the frequency, and we will get this straight line. And then if we take into account, and bear in mind this originally, here is 10, 100, 1,000, and 10,000, right? And if you take log 10 become 1, and this is 2, this is 3, and 4, after you taking log scale. And that's why this part will becomes to this form and similarly to the y-axis. So for this case, if we consider this point, okay, for this part, for this section, you can easily to see the vertical rise and the horizontal one roughly equal to 4.5 here minus 0.5. So the difference is 4, and here corresponding to 2. So this is what we expect for the blackbody spectrum. Can you follow? Can you follow? So the moon satisfy the positive 2 slope case for the Rayleigh-Jeans tails approximation. Okay, another interesting question, and measure the flux density of the lunar spectrum at a particular frequency, and given that the moon subtends at a solid angle 6 times 10 to the power minus 5 striaton, and calculate its brightness temperature. Is it actually temperature for the lunar surface? Okay, measure the flux density. So what can we do? What can we do? Maybe we can select the flux density along this line at some specific part. So if you look at the answer here, what I select for the case, for example, here, if you draw a horizontal line here, roughly this is 10 to the power 4.5, the flux density. Okay, I say again, this is 10 to the power 4, 10 to the power 5 in the middle. You see, you draw a horizontal line, and which is corresponding to the 10 to the power 4.5, and then you evaluate it, you will get 31,600 Jansky, and which is corresponding to 10,000 hertz. Okay, and means 10,000 megahertz, which is equal to 10 to the power 10 hertz. So you have the frequency, and you know the flux density, and based on the formula that we introduced before, the flux density equal to the Brightness temperature times the striaton, the solid angle, which is given to you, and you can easily to get the Brightness temperature or brightness result. Okay, the brightness intensity, which is equal to 5.3 times 10 to the power 8. Okay, and this must be converted to the Jansky into SI unit. So we got 3. You multiply it. This is Jansky, and 1 Jansky equal to 10 to the power minus 26. If you plug it back, you will get the SI unit W watt, and you put it back into this equation for B, and C is constant, 2 and K also known, and the frequency corresponding to 10 to the power 10, and all square, all taking square. And finally, we get the temperature for this moon at the corresponding flux density with the frequency in 10,000 megahertz, which is 170 Kelvin. 170 Kelvin. So it should be indeed measure the actual temperature of the lunar surface. But bear in mind, here we got as thermal radiation backbody temperature, but why we can't get such result in sometimes? Because it also the moon's surface brightness intensity will depends on the moon phase. All right, will depends on the moon phase. Full moon or the quest are not the same for different phase for the moon. And I did before in Hong Kong sky really with some differences. All right. Okay, this is the answer for question number 4. And I would like to move to other type of thermal radiation first, and I skip number 5. And may I remind you, there is another type of thermal radiation, because in astrophysical gas, the temperature is often sufficiently high, 1,000 or even million degrees. So the collision between the constituent atoms results in electron being ripped free of atoms. What I want to say, I would like to introduce another type of thermal radiation. We call it free radiation or Bam-Salam radiation. You can imagine here with an electron, okay, and with an ion here, and they have a diffraction for this positive ion, and so they change the direction, and in some sense, like accelerating or decelerating, or even have a braking, okay, suddenly change into direction, into another direction for this electron, they will produce a radiation. All right, and this German work want to memorize the pioneers' contribution. All right, this is another type of thermal radiation. Thermal radiation. The spectrum, if you look at this paragraph, the spectrum of radiation from free emission is broad, because how to say, because their plasma, there are many collisions between the charged particle and moving, and they are superposition to all together and get a broad result. And like the case in this diagram, you see in low frequency for the Orion Nebula, they follow the blackbody thermal radiation, but another part, they will corresponding to another different mechanism. And one more, like Cassiopeia A, Virgo A, this is in reverse direction, definitely not related to thermal. Okay, if not related to thermal, what will happen? We also have another emission mechanism, so-called non-thermal radiation. For example, synchrotron radiation. And what does it mean? What does it mean? We simply introduce about that. And for example, if we have some magnetic field line, and if we have an electron which is rotating like this helical cases, okay? And then if you look at other direction, head-on direction, and you will get this result. And you can use the right-hand grip rules. You can imagine, okay, this electron rotating like a rotation, or although the real path is helical path, but they produce the beam of emission. All right, and this is called the beamed synchrotron emission. And what we detect is a linear rise polarization emission. Okay, and the detail, please refer on it. Of course, the electron move very fast. In some sense, we should also need to take into account the relativistic effect and take into account adding the Lorentz factor on it. Okay, and okay, the previous few cases corresponding to the continuum process. Now we move on to talk about the spectralized process. And you see some gentlemen, as I mentioned in the first lecture, like the father of radio astronomy, like Jansky, and another successor, I will say another father of radio astronomy, Weber, okay? And he published his paper in 1940. Unlucky that this paper cannot be reached to the Dutch astronomer until they did not receive the 1940 edition until 1944. And the famous gentleman, so-called Jan Ock, nowadays in our solar system, we claims all those comets should be origin from these old cows, all right, old cows. And anyway, we are not talking about comet. And this gentleman, after he read the paper from Weber construct the first contour map on our sky. And this gentleman, the Dutch gentleman, after 4 years, he published the paper. He also proposed that someone can do the observation based on the calculation in terms of the atomic physics. And it should be some interesting result on the sky corresponding to what we so-called neutral hydrogen emission. And this type of spectral emission originally is a rare event related to neutral hydrogen. In quantum's view, probably here for this hydrogen, they have one electron and one proton, and they have a spin, so-called in quantum mechanics, we have a parameter or so-called quantum state, so-called spin up, spin down. If both electron and proton, which is spin up, and here we call it in higher energy state. And in some sense, the electron, they change their spin up direction into spin down direction. And so these changes will produce so-called a radiation, and which is corresponding to 21 cm light emission. And this, based on probability from quantum mechanics, this is very small chance. However, according to the Big Bang theory, you know, for our universe should have huge amount of hydrogen, okay, or even neutral hydrogen in our sky. So the Dutch gentleman said, based on our own galaxy, we can easily it should be easily to detect this 21 cm light. And if we convert into frequency, it should be what we so-called 1420.406 megahertz or 1.42 gigahertz. And so I will show you later our observation also based on this 1420.406 megahertz. Okay, so although the probability for this spin up, spin down transition should be very lower, however, we have many neutral hydrogen, so still we can detect it based on the prediction from the Dutch astronomer. And finally, the 21 cm light was detected in 1951. But it was to be more than 10 years before another spectral light in the radio was discovered. So, for example, in 1963, we also the astronomer detect 18 cm so-called hydroxyl molecule light, and from was detected from the strong radio source Cassiopeia. Okay, and blah, 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 blah. So these are called the spectral light detection. Okay, and then now I sum up what I say for this simple emission organism, and Dr. Swift, I leave it for you first for a short moment because I need time to demonstrate the observation. And we discussed continuum process. We also discussed the spectral light process. And we introduced the what we so-called thermal radiation and non-thermal radiation, such as the synchrotron radiation, and which is quite common in radio observation for radio astronomer. Okay, then I try to see whether I can connect my telescope. Now, please wait a short moment. Okay, I don't share the screen for a few seconds. Please do wait. Okay, please do wait. I will share the screen very soon to see whether I can connect my observatory's computer. And today, very bad luck for me. I don't know why the software for remote connection seems not work properly. Okay, I hope I can at least show you the platform for the software. We are still waiting the image. Okay, let me share the screen first anyway. Okay. Yes, may I ask you one question? Can you see this new screen?
Yes.
Okay, thank you. Thank you so much. I don't know whether you can see the fonts or for the number on this screen. And this is another computer screen that I remote control it for our telescope. And
I guess bigger fonts would be useful, but I can see them as they are anyway. So.
Thank you. I cannot change the font right now because okay, it doesn't matter. Let me tell you one by one first. You can imagine we have 3 columns for this platform. On the left-hand side, corresponding to the position of the telescope. So you can see on the lower left-hand corner, okay, we have a monitor about the location for my telescope right now, which is point to the north E position. And in fact, we are pointing to some specific object, so-called 3C48, which is a very, which is a quasar. Okay, in the middle, you will see some color, green color and red color, and this is green color corresponding to the celestial body that we can observe in the sky of our Hong Kong, okay, and red color corresponding to the source, which is set already. We can under horizon, so we cannot detect it. And on the right-hand side, the last column corresponding to the electronic signal. Okay, and now probably I try to point the telescope to Orion A. Okay, I double click on the Orion A, and if it works, here at the bottom you will see some message, so-called slewing. Okay, the antenna will move to some specific direction so that they can point to the source. Maybe the connection weight not very they are not properly well, very slow. I don't know why. Anyway, right now you can see on the lower left-hand corner the little red color little move a little bit. All right, because Orion A right now in our Hong Kong sky, which is in the southeast direction, and the angle of elevation corresponding to 62 degree. Okay, and then once they point to the source, we can set up how to create a map for this object. And for radio astronomy observation, we have several modes. One is like what you learn in optical method. You just point the telescope to a specific target and monitor it continuously. Okay, this is a simple method, so-called tracking. But we also have another interesting method, so-called OTF, on the fly observation mode. Okay. Let me see, the response is very, very slow. The connection. Okay, in this case, then I don't wait on it. Okay, I I switch to other screen first. Let me see. Not this one, sorry. Okay. Very sorry because our connection not very good. And here is a YouTube video, although the image with poor quality, but we would like to demonstrate some result to all of you. So you can see, okay. First, may I say a few words here corresponding to the sun that we kept not captured by myself. This is captured by VLA. All right, this is captured by VLA in 1980 something. Okay, and what we do here. Wait, let me start it for this video. And now, please wait a short moment. Please wait a short moment. Okay, we move on to this page, and here we have a mapping method. We want to create a map or a photo, I would say. Okay, and this photo corresponding to, let's say, 7 row times 7 column, in total 49 pixels. You may bring me 49 pixels. My, let me, wait, 49 pixels, you showed me a very poor resolution photo. Yes, 49 pixels, because for the single disk of observation, we try to move the telescope physically. Here we can show you the telescope which is moved physically. On daytime, you can see the shadow for the sun, right? Maybe very slow, the transmission through the internet, but anyway, you can easily to see the shadow which is moving, right? Which is moving. And then, which means the antenna is physically moved in some specific direction, Can you see that? Can you see the telescope which is moving?
Yes, we can see the video.
Okay. Thank you. Okay, so you can see that this is another mode of observation for single disk observation, even for very big radio telescope. Let's say in Shanghai 65-meter telescope, we also use this method to do observation for M31 and M33. Hope we detect some signal corresponding to the dark matter annihilation at the time. Okay, anyway, so the antenna physically move is a method so-called OTF. And finally, what will happen? And we can get the following result. Can you see that? We fill up 1 pixel. For this case, this is monitoring to our sun. I just create 49 pixel images. Okay, so first at the top left-hand corner, and then continues, move to the second pixel, third pixel, 4, 5, 6, and 7. Once they finish the first mode, they move on to the second mode, just like the kids, they do coloring some pictures, okay? And finally, they will fill up a picture with 7 times 7 pixel, 49 pixel. However, what I want to say, not every picture that we create corresponding to 49 pixels, we can increase the number of pixels, so-called higher resolution. We can increase to few hundreds, okay? And see whether we can show you the final images. Yes, here. Okay, and this is our result, and we do it a simple reduction, and we can find this is our sun. This is our sun, because at that time we point our telescope to the sun, you can see the shadow. If this is not our sun, then that's good. Okay, maybe we have another interesting object. Okay, now apart from this observation, may I remind you that we can capture the signal. We can capture the signal. So once we capture the signal, and then we can do some simple processing. So the last part, I would like to show you the simple processing result. And first, you need to install software, so-called Anaconda and Python. Okay, let me open it first. On the menu, I press PowerShell prompt. Okay, with Anaconda, and then I put my Python programming in. This is a DOS command. You can easily to see Python folder here, and then I entering to this folder. Okay, and I can call what we so called the Python program, and Jupyter. Okay, Jupyter notebook. So first, you need to install for this Anaconda and Python programming, and then you enter on it. Please do wait. Let me call some program come out, and then we click on to the Python. Yeah. Yes, this is the web-based. Okay, and then I have to link or file here. One is in case I fail to run the code, at least I show you the result in our computer for my teammate. Okay, what we have. Okay, now I click on to this radio demo underscore English, IPYNB. Okay, PY corresponding .py corresponding to a Python program. I didn't know before personally the Python program until I asked someone help me to give me some data and file. They all given me the file in terms of .py. Okay, so I start to learn about that. So I will encourage all of you, no matter what age you are, please do not scare and do not mind to learn Python programming. Okay, first, free of charge, and second, most of the code are very higher level. So I mean, we can easily to understand, for example, like the first program, okay, input something and import something, right? And finally print out something. Or even Python program, if you never pay before, you put 2 plus 3 and press enter, probably you will get 5, similar to our calculator. So I will say not too difficult to learn. As far as I know, in Taiwan, they are class 3 students start to learn Python. Okay, all right, and so for program 1, just several codes, and then if I click on it and press Shift Enter, then you can see the result to show you what is the corresponding position for today for our sun, which is located in the constellation Pisces. Let me magnify it much better. All right. And this is a simple program. First one to specify the position of a star or planet. Okay, you can convert the time and even the object. And this code, which is I mean, lowly you create by yourself. Some people they upload in somewhere you can download it very easily. Okay, and the second one we would like to show you related to our Hong Kong case. Okay, first, you can see this representation LAT and LON corresponding to the latitude and longitude. for our Hong Kong, let's say the latitude is around 22.24 north in the latitude, okay, and longitude is 114 point something. And our telescope, the height with respect to the water level, so-called altitude, is around 4.6 meter. Okay, and the UT, this one probably not today, but it doesn't matter, okay, as a demonstration. Okay, suppose an object which is located in AZ, azimuthal position and elevation with this result, and we convert it to radian, and we import some library iframe and numpy, and then we can easily to run the code and see what we get. Press Shift Enter, and then we can show you today's yes, I changed, and my friend changed this Julian day already corresponding to today, and this is UT. At that moment, the sun's position changed from so-called azimuthal coordinate system into equatorial coordinate system. Okay, and next, we would like to demonstrate, like what I want to say today is, after we did the observation, we have a fixed file. We have a fixed file for our small radio telescope. Very lucky, it was made in Italy, and the Italian create the output format, the data structure in terms of fixed file, and FIT fixed is compromised data structure in our astronomical field. So we would like to show you how come we can import some module and then upload the radio file to do some processing first. For this 1, 2, 3, 4 up to 14 code, we introduce what we so-called NumPy and AstroPy to our program. Okay, we import on it and Shift Enter, and then now we import the necessary module already, and next we need to upload a radio data file. Can you see this red color data files? This is what we capture in our Hong Kong sky in 2021, and the image for SGRA corresponding to our Genetic Center, Secretariat A, and dot fits. So we upload this file in our directory on the C drive Python program for the user already, okay? So assume we finish our observation, we have this file, and we can replace this file to our observed file and press Shift Enter. Okay, and next, you upload this file to the Python program, and HDU corresponding to read out the header for the file. And yes, as I mentioned before, this is a standard format for the fish file. So maybe here you can easily to see some days of observation and end time and start time, and which object and the corresponding position, and and some value, and this value corresponding to the pictures, each photo with the corresponding value. Okay, and here also have some information about the beam size for our telescope, okay, and which frequency and etc. and polarization left and out, and and then continues. We look at the data, and my friends create this file to put the picture corresponding to each pixel with a value and form an array, and this is a 2D array corresponding to the image that we collect. And next, we continue to import some plotting library. Okay, now this is the wall picture. Can you see this wall picture, everyone?
Yes.
Okay, Gwen, thanks. And you can see here with a bar corresponding to the value, okay, and different color corresponding to different value, and also corresponding to the different intensity. In fact, this is the wall images for our galactic Sagittarius A galactic center, okay. But you may say, Sing, this is not like a galactic center. Yes, this is a wall data. Okay, please be patient. We will continue to show you the result. Okay, and now please do wait. I run the program already. And continue, right? Yeah. And then I continue to pass and yeah. And so wait a short moment. Yeah. Okay, yes, we finished the simple processing, okay? And we do some interpolation between each pixel, okay? So after this processing, can you see that from the left-hand side, we have the wall images. On the right-hand side, we can easily to see the galactic center, okay? Of course, we cannot see any black hole, okay? Our telescope is very poor in sensitivity and very small. However, very lucky in our local Hong Kong sky. Very lucky the galactic center, to be honest, usually not higher than 35 degree in elevation. But lucky our site can look at this galactic center. And so we capture this result. And you see, I passed several, I won the program several times, because you see from this figure, we also have some description. For example, the object's length and the bandwidth and the days for observation start time and end time, and the beam size for the telescope, and the left-hand side and right-hand side polarization and size. All right. So here corresponding some result. And may I also indicate some interesting object here? And probably this pixel at that time very frequent in our site. We can detect the Starlink satellite. Okay, so they gave us trouble. Okay, probably we can artificially remove it. If we confirm this is a Starlink satellite, we will remove this raw data pixel by using some averaging for the corresponding pixel. We can artificially fill up this to remove it. And why I say this is Starlink, because you see this contour line, which is very uniform and dense. So in this case, this is some artificial object rather than the natural object from our sky. Okay, so this is a simple demo. How come we can got such a poor resolution picture, but still we detect it, and also here corresponding to our historical detection in our Hong Kong sky. Of course, Hong Kong is a business-oriented city. If you talk about astronomy or even radio astronomy, no one care about you. And they also from day to day look at the stock market. Okay, I think near the end of today's presentation, okay, and any question you want to ask me, yes, please let me know and welcome. Oh, okay, someone asked me, send us the recording. Where can I find that? Please do wait. maybe Miss Kong, she asked me a good question where I can send us the recording. In fact, yesterday I upload to my YouTube channel. I upload successfully, but I don't know why they not display. Very quickly, I think I need to ask my colleagues to help so that I can tell you the name in YouTube for lecture 1 as soon as possible. And today we have lecture 2. And Dr. Baga, do you mind I upload it on YouTube, the video?
Of course not. If you can do that and then give me the link, I will share it with everybody.
Okay. And I will send you a link as soon as possible. You can also share to the fans from Romania. Okay, yeah. And also I will see whether I can upload it on YouTube successfully, and then we'll let you know, Miss Kong. Yeah. Any other question? May I obtain your email? Oh, yes, you can. My email is here. Okay. Or you can easily to search it in the Hong Kong PolyU Department of Applied Mathematics website. You can easily to send me the email. Okay. Originally, we are very unlucky last week because if you see this picture, don't look at me, this man not important. The most important thing is the second radio telescope. Here, you can see this photo. The feed horn has already installed on the biggest telescope. This is 4-meter new, I call it second radio telescope in our observatory, corresponding to 4 meter in diameter, more higher sensitivity. Unlucky that we failed to do good protection and let the motor containing some water so that while cannot be moved. And we hope we can use this one to detect pulsar in our Hong Kong sky. Of course, 4 meter in diameter is not a good size to detect a pulsar. According to the company and our calculation, probably we can detect 1 or 2 strong pulsar in case we are lucky. Otherwise, I want to show you today, but sorry, they failed to work. And if we will plan to install a camera here so we can show you the real-time result if possible. Yeah. So the second one is prepare to observe some pulsar for educational purpose, and also very important with more radio telescope, because sometimes if 2 telescopes point to the same position, we may have some interesting judgment and discussion between those telescopes. Okay. And bear in mind this textbook. Last week I asked you to find this textbook or to borrow this textbook from the library. Although I did not upload, did not send you the question number 2 and question number 3 solution, we will do it very soon. And all the material based on this great gentleman's textbook, so you can search on it. All right. And yeah. Okay, let me see other question. Okay, if you have question, welcome to send me the email or tell me later or voice out here. And bear in mind, yeah, may I remind all of you, next week, another expert will teach you more interesting object and corresponding to what we so-called an array. Not only use one single disk observation, and very interesting, I think, yeah. And so-called radio interferometry. Yeah, this is nowadays the forefront instruments. Yeah. Okay, if you don't have any question, and I think that's the end for today's presentation. Thank you for joining this lecture and see you on next week. Goodbye, good luck, and good health. Bye bye. Okay, see you. Bye bye. Goodbye.哦，新加坡嗰個老師都喺度。係啊係啊，你
我在你上次
係啊係啊。
哦。